Hi everyone, welcome to our tutorial on Bayesian value-based recommendation. I'm Flavian, Vasile, and these are my co-authors, David Rohde, Sergey, Ivanov, and Otmane, Sakhi. So the contents of our tutorial are split in 4 parts. The first part will be an overview of existing work. So we're going to cover 2 things: the problem of continuous improvement of recommendation systems. So we're going to just look a bit of kind of the life cycle of improving recommendation systems and what does that entail. And based on this life cycle, we're gonna highlight the difference between organic and bandit-based recommendation, or what we call classical versus modern recommendation. This is something that we presented last year in our previous tutorial at RecSys Summer School 2019. And we feel it's an important stepstone. So once we have this kind of covered, we're gonna go over new material. So this will be looking at recommendations through the lens of decision theory. So this will be kind of the first thing we're gonna try to define. We're gonna use these new concepts to classify again a recommendation now in a different way. So we're gonna show the difference between true and proxy reco approaches. And then we're gonna finalize the second part by showing the interplay of the 2 ways of classifying recommendations. So the one we introduced last year, the organic versus bandy, and the one that we introduced right now, which is true versus proxy. And we're gonna show how these 2 ways of looking at recommendation play with each other and how they help each other. Once we have this kind of classification done, David will take over and he will present our more recent work on BLOB and BLOOD models. This is work covered in one of our latest KDD papers. And then in the last part, we're going to go over a practical session, and then Sergey and Otmane will go over a couple of notebooks in Stan and highlight ways of doing Bayesian record. So that's kind of for the content. So let's get started. So on the overview of existing work, the first thing that I want to cover is kind of to motivate the whole tutorial is to show a bit how we think about the life of an ML researcher in his daily activity of improving a recommender system, right? So here's the researcher, and here's the kind of the overall system. So on the left you have the online system represented in its behavior by PyOld, so the existing policy, the existing recommendation policy, and this system will interact with users, right? These users will be represented to our system by a context. This is step number 1. And then in step number 2, fully described by the PyOld, we will choose an action. So this is the second step of the interaction. And then the user prompted with a recommendation, this is what the action is. It's really recommending an item or a set of items. Will choose to interact or not with the recommendation. So it will he will remit a reward to our system. So this is like 1, 2, and 3, and then all these interactions and all the features and everything are being logged to the offline system. We're going to have some big database, maybe a Hadoop cluster, a Vertica cluster. We're going to have all these logs of offline interaction, of historical interactions. And of course, we should have a representation of the PyOld in our offline system such that we can compute offline metrics. So this is what we have. And then, of course, our main objective is to create better recommendation systems, right? So we will try to improve on PyOld and create a PyNew model, like a new policy. And of course, the first thing to do, we'll compare PyOld and PyNew on these offline logs and with these offline metrics, right? And we'll do this until we find something that is better than PyOld in offline metrics, and then decide to go to an A/B test, right? So this means that now we split the population, so we split the users that are incoming in, let's say, Pop A and Pop B, and we will run an A/B test comparing the performance, the online performance this time, of PyOld against PyNew. And finally, we'll be very happy when PyNew is better than PyOld in online performance. But no matter what, we will still try to do even better. And this is basically what we call the life cycle of recommendation system improvement. So yeah, at this moment I will take questions if this would not be recording, but I hope this is quite clear for you. And I hope you agree this is in grosso modo what most of the companies doing recommendation systems do as an activity and as a setup. Okay, so one thing that we see here is that in order to improve the policy, we need these rewards, right? So that means that somehow we shown to the user some recommendations, right? So the question is, of course, how do we create this first pilot, right? How we create this first recommender system from scratch, right? We don't have any past user feedback on recommendations. We never had recommendations before. How do we create that, right? So this is the goal of the next subsection, is to highlight the differences between creating a recommendation from scratch and improving on existing ones. So again, the same figure, and then pi old and pi new. What we see and what we shown in our previous tutorial is that we have these two important steps. First, we need to boost up an initial policy pi old without user feedback, because we don't have such a thing. So we call this existing user activity, organic user activity. So this is user activity on our online system that is that precedes recommendation. So since let's say that you would be an e-commerce website, it's the user activity, the user shopping activity on its own, and then all the way to sales. And then, so this will be used with some additional assumptions to create an initial recommendation system. And of course, once we have this, we will start logging the user interacting with the recommendation systems, and then we'll create bandit user feedback, which will be the second step of our recommender system life, where we'll start actually using this new bandit feedback to improve pi old, or the set of pi old systems with better versions. So what we did in our previous tutorial, we called this first type of recommendation classic recommendation. So something like collaborative filtering, next event prediction, all these kind of approaches we argued that are falling in this kind of classical reco, where the goal is to model the user activity on its own without recommendations. And then more recent work on modern reco, when once we have actually bandit user feedback, feedback that is on the recommender actions, then we can use this feedback and further improve the policy and replace it with Pioneer. So this is what we call modern reco. So let's see an example what we mean by all this. So in classical reco, we argue that, for example, a user going to a e-commerce website has a certain trace of activity, a certain product timeline, let's call it. So let's say that the first event he will have on our website, it's this V1, and he will visit a beer, and then he will see at the time step 2 a phone A, and then a phone B. Now, already we can create a supervised task out of this, which is kind of a next event prediction task, right? We will look at the past of the user, like what activity did he have on the website, and try to predict what he she will do next, right? So we have now a transition model for our user sequence, let's say, on the website, right? So it's very close to, let's say, a language model, right? So when you try to compute the probability of next word in a sentence, it's a very similar task, and a lot of work has been borrowed from the NLP literature for user sequence prediction. We did ourselves. So of course, then now that we have this kind of user activity model, so we can predict what he'll do to times 3, we can actually have a kind of a probability distribution over next events. And now that we have this thing, we can actually kind of falsify it and look at what actually happened, and actually, have a fully supervised task here, right? So that's quite nice. And yeah, of course, we can basically close the loop and continuously improve the language model. And then the question is, what do we do with it for recommendation, right? Because in recommendation, we really are interested in a slightly different problem, which is the user saw these 3 items, V1, V2, V3. And now we're asking ourselves, what should we show as a recommendation? Should we show him couscous? Will he click on this? Will he click on a phone B? What item to recommend here? So here is a CTR prediction problem most of the time. What will be the click-through rate on any of the items that we could show in a recommendation, right? So this is a slightly different problem. So to recap, we have this kind of next event prediction model where we can predict the natural occurring user behavior, the organic behavior. and this probability sums to 1, right? The user can only do one thing at a time next. And of course, what we want is actually n CTR models, right? For every action, we have basically something that goes from 0 to 1, ideally. So they're not mutually exclusive, and they're actually trying to predict the CTR when taking an action. And this thing we don't, in the first beginning, at the beginning when we don't have a recommender system, we don't even have evidence for, right? We never shown recommendations before, right? So this is what we want, and this is what we have. So now, of course, when we use a kind of a next event prediction model for a condition, we are making an implicit assumption. We're saying that here, for example, this is the high, the phone B is the most likely product to be visited next by the user. So why not recommend it, right? So what we're really saying is that we're making this link between kind of the user affinity to products in the website and his CTR on products if they would be in ads or in recommendation. So there's a lot of literature in recommendation that makes this assumption implicitly. But of course, this leads to a discrepancy between offline metrics and online metrics, right? You'll have ranking metrics offline, and then you'll have basically a click uplift or number of sales uplift online. So when you optimize for one, you might not optimize necessarily for the other if this link starts breaking at some point in time, this partial ordering. So now to recap, when we look at the problem like this, when defining the difference between the two as being on the type of signal that the policy is leveraging, we can see that there is a classical approach and a modern approach. The classical approach is more about starting, like creating kind of the first versions of recommendation system and not being worried about the feedback that the users give you on the recommender system itself. So this is quite normal, right? Because at the beginning you cannot worry about the feedback if you don't even have a recommender system in place. And then here you see all the work on missing link prediction, next event prediction. So this is kind of the traditional tasks, and it's quite nice because also, you can write paper on it. You can have like a data set that you can open source. So a lot of people can work in parallel on this and to improve this. And then, but it has the limits because it doesn't actually optimize for what you care about online. And then, of course, you have the modern approach where people start looking at the clicks on recommendations, and you're trying to increase the clicks rate. And here, most of the time, the problem is framed as a click likelihood problem or a contextual bandit or a policy learning problem. And we'll get back to this. So this is what we presented last year in our RecSys summer school tutorial. And what this year we want to bring further is actually to add an important distinction within the bandit, especially within the bandit recommendations, right? So we feel like even within them, there are some methods that are really optimizing for the online performance, and some that are still proxy methods that they need additional assumptions to actually have a clear link with online performance, right? And this is the goal of this tutorial, to highlight this difference and also to propose some methods on the Bayesian value models. That will be in part 3. So first of all, let's look at recommendation through the lens of decision theory. What would that mean? This will help us make this new difference. So in order to map recommendation to decision theory, we need first to understand a couple of basic concepts and then find them back in recommendation. So first of all, in decision theory, we have a model of the world that describes how the world will react to our actions. And this, in the recommender systems, for example, for click prediction, would mean having an explicit model for the CTR. So given an action and user feature vector, let's say V, what will be the click-through rate, the probability of a click on that pair? So this is the model of the world. And the world here are basically the users. And then, of course, the goal is to find a decision rule or a policy from a set of admissible solutions. So let's say we have the space of exponential policies. We would like to find the parameter vector that optimizes our performance, that basically maps for user history maps it to a set of actions or to a certain action that is optimal, that has the highest CTR. And then finally, the first part, the model of the world, talks about basically the reaction of the world. And here it's basically a number of clicks, but then we can make the difference between actually the reaction itself and the utility that this reaction has for us. For example, for an e-commerce website, it might not be actually number of clicks that you're interested in. It could be actually number of sales post-click, or could be actually the full sales amount driven by the recommender system, like caused by the recommender system, or even the pure profit, right? So subtracting all the costs. So this will be the utility function that we put over the whole thing. And this is, in the end, what we measure in an A/B test will be really, what is the impact on the bottom line of the business, right? So ideally, this is something you should measure directly in the offline performance if you could. So why do we think this mapping to decision theory is important? First of all, because it allows this decoupling, explicit decoupling between the reward model, or the kind of the external world model, the policy, and the utility function we put on the reward. And because it's kind of an existing body of literature and it's quite advanced, I think it provides a unified conceptual framework that we could borrow concepts from, and help clear a bit the way we think about recommender systems and what their objectives are. And we hope in the future it will allow us to port some of the advances in decision theory to recommendation and even back. And I think we already got started a bit with our work on distribution robust policy optimization for recommendation. This is work that we did last year at AAAI. And there is some follow-up work that, if you're interested, you can see at Reveal, a workshop this year in RecSys. Okay. So now let's say that we have this very simple problem. We said we want to optimize, let's say, the number of clicks. It's quite easy to see that in this simplified case, and if the utility function is just kind of number of clicks, there is nothing on top of that. It's very simple to see that the optimal policy is to deterministically find the best action, best arm to play for every particular V, for every particular user. So you find for each user the ad or the recommendation that has the best CTR. Of course, this assumes a lot of things like ID, kind of like non-fatigability, like you want to buy the same product over and over again. So there are many assumptions hidden here, but of course you could map all this uniqueness into the user state. So the user, it's never the same twice. And then we'll still have that actually you could create a deterministic policy that for every particular user, there is this certain action that you need to play, and this is the optimal policy. However, a lot of times we're interested in differentiability, so that means we want to make this policy non-deterministic. We want it to make it stochastic. So that leads us to this very important equation that I think we should concentrate upon quite a lot. It's not that hard to understand when you go past the notation. What it says, this is a generalization of the previous equation, where now the best arm, it's not alone, right? So you now have a distribution over all possible arms, right? And you are trying to find the policy that optimizes this quantity for every V. And now, of course, weighted by the probability of V arriving to our system. So this is just something exogenous to our system. It's just the probability of seeing users of this type V. So once we have, for this particular user, we can only look within the bracket, square brackets, and see that what we want is really to maximize the probability of click over all actions. And what we control is this pi theta, right? So we are trying to find theta star that becomes almost close to the deterministic policy that we had before, to argmax around the best action for V, right? That maximizes the click. So why do we care of actually being stochastic and being defined everywhere. Well, this is quite important for differentiability when this is something that is you want to optimize overall with additional components. So this is something like an end-to-end learning and things like that. This is something quite helpful. But also it helps in very practical manners, like for example exploration. The argmax that we had before assumed that we actually know and we have seen all actions for all users, and we know what is the best action to play, right? So in exploration, this allows us now to actually draw. This policy will allow us, despite theta, will allow us to draw actions that are not necessarily maximizing according to our current knowledge, but that could be good candidates for it. So this will help with exploration and also with counterfactual reasoning. So that means that you could use data from an existing policy to simulate data from any other policies using the importance propensity sampling trick. So there are quite a lot of reasons for this to not be deterministic. So from now on, we'll assume that it is non-deterministic and it's stochastic. So this will be our formulation of optimal decision or optimal recommendation optimization problem. Now, looking at the mapping to decision theory, we can see that this equation models the relationship between the world model, which is again the CTR model. So how will the user react if we play a certain action? Will he click or not? And then the decision rule or the policy, which is the pi theta. How much should we play this action given this user? And the utility function. In our case, the utility function is 1 because we just want to optimize number of clicks. So it's implicitly present, but you could have actually a full function on top that gives you the final utility, and this will be the quantity to be optimized. So yes, so now that we have this equation 1, the distinction that we want to make further versus our previous tutorial is that we will call methods that directly optimize for equation 1 true methods, and then any other method that doesn't fully link itself to equation 1, or it links itself to equation 1 with additional assumption, as a proxy method. And we will see why this distinction is important in the last part of section 2. But first, I would like to go a bit over how to compute this CTR model, and we will show that there are two ways. There are the value-based approach and the policy approach. So the value-based approach actually has an explicit model of the world, so of this p-click given action and v, the user. And then, for example, here we show how a Bayesian model would look at the situation. This is basically what we'll look in part 3. So basically, we integrate over all possible thetas from the family of function that we care about, and we will have a model of the world defined everywhere. So for all actions and all users. Alternatively, there is the whole class of policy-based methods that produce an estimator of the click by just, again, kind of reusing the data, the log data from the current policy, pi 0 or pi old, by just basically the inverse propensity sampling trick. So here you see that we have the number of clicks that we have in the current we saw in the current policy by playing action aj and on the user vj, and this is the propensity, the probability that we did this, and this is the number of times the vj appears. So if you multiply these two things, you'll get the expected number of times we shown this item or this ad to this type of user, and this is the click. So you'll have number of clicks over expected number of displays, so you'll have a CTR. Just a side note, this is not how like this. We separated in parentheses slightly differently than the normal IPS formulation or the normal policy formulation. Most of the time, you'll have pi theta over pi 0 as a fraction, and not have them separately. But we feel that this new basically regrouping of the terms in equation 1 shows this clear difference between what the policy and what the value-based models are doing. So they have basically different ways of estimating the CTR model, and then on top of this, you'll have this value maximizing policy pi theta that will stay next to it in order to maximize the whole thing. So you'll have an Rmax over the whole thing. So yeah, this is how we look at the value versus policy methods. And now to wrap up part 2, I wanted to just show a bit how we can use this new classification and how does it play with the old classification. So this is kind of the most important figure. So before, as we said, we were thinking of recommendation as being either an organic task or a bandit task. And now we're introducing this new classification, which is true versus proxy method. So is the loss really trying to approximate online performance or not? And not is not really not, it's just not directly. So let's go over all possible combinations. So we are arguing that there are no true organic task methods. So you cannot optimize for online performance directly by using organic data. So like next event prediction and things like that. You need to make this additional assumption. So it's in by definition a proxy method. Then within the class of true bandit-based methods, so all these true methods are bandit-based. All methods that are true have to be bandit-based because this is the only measure of true performance that we have. We have these 3 subtypes. So first, the value-based ones, so logistic regression Bayesian approaches. There is a whole literature on this. So this is traditionally kind of the purview of like the computational advertising literature. So we have large-scale logistic regression for CTL modeling, and high-log linear, gamma Poisson models, more recently factorization machines. There is a huge body of literature for this. Then there is this kind of subdomain where debiasing or taking into account the logging policy when doing CTR modeling becomes important and is highlighted. And this is some of our work was in RecSys 2018, for example, on causal embeddings, is in this kind of vein. And then finally, this is kind of more recent work where you have fully Bayesian models for CTR, and this is will be covered in part 3, and this is material based on our KDD paper on BLOB. So yeah, check it out. Okay, so this is value-based. Now let's go to off-policy-based CRM, POEM, KLDRO. These are things that are falling mostly in what Torsten Joachims introduced in 2015, the counter-risk minimization framework, with the first algorithm, POEM, the policy optimizer for exponential models, and then some of the extensions, the SNPs extension, and then some of our recent work that makes the link between CRM and distribution robust optimization, which is quite an active subfield of or a method used in decision theory. So this is one of the links we made, and the resulting algorithm KLDRO. So this is all things that are about creating kind of offline estimators of online performance and then optimizing using kind of the IPS trick, optimizing the value. So basically playing more the arms that look promising while controlling for variance. And then of course there are the methods that try to blend the two, the joint approaches. And here most of the work is on doubly robust methods that combine policy and value-based models, or some approximation of that that are not necessarily doubly robust, like our work on dual bandit from last year at Reveal. So these are kind of the subtypes of true bandit-based methods. And then, of course, we have the classical proxy methods, where we have all the collaborative filtering via matrix factorization, where the metrics are reconstruction error. And you have SVD, non-negative matrix factorization, field-aware factorization machine, more recently variational autoencoders from Netflix. And then kind of on the more ranking kind of task, when you do next user event prediction, we have kind of, again, starting to kind of borrow from language models. We have kind of ProtoVec, which is kind of a port of OrthoVec to product timelines, and then MetaProtoVec, also some of our work, Bayesian personalized ranking, BPR, and then fully neural nets, RNNs for this, 2D, CNNs, TCNs, attention models, you name it. So this is very kind of very classical, very well established, especially in the academic literature. This is the standard task, and this is what we've been criticizing recently as being not necessarily in line with online performance. And this is, I hope, showing why. Finally, we have another class of methods that are not obviously proxy methods, but since they are bandit based, so they use actually recommendation like interactions, so basically past clicks. These are the click ranking methods. So this is the subset of literature that I think is inspired from like the search optimization literature, especially the learning to rank, where actually we are in the setup where the recommendation is actually a set of items. It's returning a set of items, and then we're trying to rank higher the actual clicked item versus all the other items because we consider them as being negatives. We think this is actually a proxy method because in order for this to be fully aligned with online performance, you need to assume some particular form of the utility function. Because in the more general case where, for example, the utility of the banner is non-decomposable of the list, for example, you have a click because the interplay between all of the items, then of course you cannot use any of the items as negatives, right? So then click ranking wouldn't be the thing that optimizes the banner performance. So this concludes kind of the classification of recommendation according to true and proxy and bandit and organic dimensions, and hopefully this is quite clear. Now, why do we think it's quite important to talk about these differences between proxy and true? Well, because they I think they represent some form of trade-off between bias and variance. Proxy methods are very easily measurable, and they have good offline estimators, but they're biased in the sense that they're not fully aligned with the online performance. And then true methods are trying to approximate online performance, to predict it, but in many cases already it's quite hard to measure online the treatment effects. Like we need to run an A/B test for like a couple of weeks to measure significant changes, especially once the systems are mature, and it's quite hard to make big differences in the updates of the policy. So then, of course, the offline estimators of this online performance, they will suffer from noise, though they will be unbiased. So there is this kind of, let's say, bias variance trade-off between the two methods. But then again, proxy methods can be really quite powerful, and this is why I think they take most of the space in terms of like online systems, like real systems, real recommender systems, is because when the assumptions, the simplifying assumptions being made are quite aligned with reality, they become really powerful. But having said that, I think true methods, in the long run, they will prevail. But they need this additional organic signals. So I would say that the future is mixed. And I think the message of the end of part 2 is that we need organic, and we need to borrow from these proxy tasks, and we need to find ways to do it. And this is a good segue, I think, for part 3, where David will show how we can use Bayesian value models to do exactly that, to borrow evidence from the organic signal to improve our estimators of bandit performance. So this is my cue. Hopefully this was interesting to you, and thank you for listening.
Hello, everybody. So Flavian's already taken you through the differences between the proxy, policy, and value-based methods. And he's really explained to you that a lot of what you'll see in the recommender literature is really a proxy-based. It's looking at a signal of patterns of users' behavior, identifying correlations, and then completing them. And this is an interesting signal, certainly, but it's not going to give you some absolute indication of online performance for a metric that you might observe online, like click-through rate. Instead, you've got organic metrics like recall OK and metrics like this. And in order to get some sort of forecast about how different policies or different algorithms that you might deploy in practice might perform, you need to use some sort of true method that's going to give you some notion of the actual value that you're seeing for the recommended policy on things like click-through rate. And in order to do that, you really have no choice but to look at the recommended system logs and the outcomes of recommendations you've delivered in the past and whether or not you obtain reward on them or not. And we can see that, like, okay, this is clearly a very valuable signal because it's giving you something that's not just an ordering and an imperfect ordering, but an absolute measurement of the value of the methods. But we can also see that there's a real risk with this, or a real difficulty with this, which is the signal is very uneven. So on some recommendations that the previous recommender system favored, you'll see this many, many times, and you'll get a good signal and a good estimate of the click-through rate on these particular recommendations or actions. And you'll also get some exploration on some other items, but it's usually very sparse. And then there will usually be a massive part of the space that's completely unexplored. This is, of course, partially due to the fact that you've got a randomized policy, but focusing on what your previous system delivered to be good recommendations. But it's also simply because the space of recommendations is usually very large. And when you take into account the fact that you're doing personalizations, it's impossibly large. So in this section, we're going to say, as Flavian said, the future is mixed. We're going to look at how to combine signals from organic models in order to try to get a good prediction for the click-through rate as best we possibly can over the entire space. So in order to do this, I'm going to introduce some models that we've recently published at KDD, the BLOB and BLOOD models. And the BLOB is the Bayesian latent organic model, and it's, of course, simply an organic model, and the BLOB model is Bayesian latent organic bandit model, which we'll go into in more detail. In the subsequent sections, we will take you through a tutorial on how to implement simplified versions of BLOB in both in Stan and in TensorFlow. So I'm just going to quickly go through the key example that we're talking about here with 5 products. And we're seeing a user without any interaction with the recommender system are going to view products. So they're simply doing some online shopping and they're viewing item. What we usually think of our organic model is, can you predict an item as they do this like this? So are we able to predict that a beer may follow couscous and rice? The recommender system problem that we're interested in, the bandit signal, is going to be, what is the probability of reward or click if we then recommend each of these items? And as Flavian has explained in the previous section, these in fact are quite different problems. Of course, they're different and they even have different support. The first problem, there are P probabilities if there are P items adding to 1. And here there are P items, each of them between 0 and 1. Also, we have the challenge that we probably have almost no recommendations of the phones like this to sequences that look like this. Very few, very likely. We may have recommendations of all of these because we're not quite sure what the best one is. So we can utilize the bandit signal here, but we might well have nothing like this in the bandit signal history. So we need to do our best to come up with good estimation in these settings. I'm going to now jump into the BLOB model. As I said, it's organic, so it's really building a user representation of this and making sure that we can predict this item given the others, at least as best as we possibly can. So this is the intention of the model. In some respects, not particularly novel, but it is a fully probabilistic model, similar to other models that you will have seen in the recommendation system community. The model is based on the idea that we've got a user representation, omega, and this is a vector of length k, showing the user's interest in k topics. We're going to sample that from a standard normal distribution, giving us a matrix at k by 1. We then have the user representation psi. So which is, well, if we have p items and a latent factor size of k, this will be a p by k matrix. We multiply it by omega, giving us a vector of length p, and also a bias term rho. We apply softmax to this, and it gives the next item probabilities, each of them being p numbers summing to 1, and then we can sample the category of the items like this. And what you're going to see as you do this, and I'll explain this in a little bit more detail in a second, is that when the dot product or of the user embeddings is high, these are similar items, and we're going to see them occur together in different user sessions. So each user, we sample this, and then we will do a multiply, and we can have a user history of any length. From a graphical model perspective, we have the graph here. We have U users. Every user has their own latent representation. We have the embedding and the bias term here, and we can take variable length sessions for every user here. It's a very similar model to some you may be familiar with. The multi-VAE paper from Liang et al. Had quite influential, and this model simply replaced the linear model here with something that's nonlinear. The latent Dirichlet allocation model doesn't use the softmax here. In fact, it does this with the psi times omega without any kind of softmax, and has simplex constraints on both psi and omega using Dirichlet priors that keeps it on the simplex and makes it okay without applying a transform. So to demonstrate an example, we can imagine after we've learned our embeddings, we might see that they look like this. So here we've got a number of phones. We've got the sleek phone, the city phone, and we're seeing the dot product of these two are similar. And in fact, we can also identify that the first component here is clearly a phone component. And we're seeing that they both have high values within the phone component. We have couscous and rice. These have high values in the grain component. We have beer. And beer has some value in the grain component, but is primarily out there on its own. And we have two items of clothing, female and male shirts. And these have their own categories, but are anti-correlated. We also have a bias term that we're going to ignore in this example. We'll set to 0. And we can see we get very sensible behaviors. So here we're viewing two algorithms, MCMC and variational Bayes, that give very similar results for our embeddings as we view items. And so this is showing us, imagining these are fixed, we're going to say, okay, we've got these items here, we already know psi and rho, let's solve the inverse problem and discover the user embedding here. And we see we get pretty sensible behavior. If you've seen one sleek phone, the phone embedding fires, there's a significant amount of uncertainty and the other embeddings remain fixed. Here we have more instances of phones, there's less uncertainty. It's very clear that the user is interested in phones and less interested in other items. And if we have even more items in history, this becomes even more confident. We can look at other examples, perhaps a history with multiple different types of items here. Here we've got two female shirts and one sleek phone. As a consequence, we see the phone embedding fire, but not very strongly. We see the female embedding fire more strongly, still a certain amount of uncertainty here, and the male embedding is showing the opposite trend, and there's a certain amount of certainty here that these are different. So, as I said, this is a pretty traditional model. We can do pretty traditional organic testing whether we can autocomplete correctly. Here we're showing, using simulated data, the record gem simulator, that we are able to autocomplete quite efficiently on this data here. And it performs well against baselines such as popularity, IDEM-KNN, and recurrent neural networks. And so there I'm going to draw a line under the BLOB model. It's just a particular way of producing the organic model. It's not the only thing you can do. We'll actually use something simpler in our example notebooks, but it's a reasonable way to produce a latent representation of the user's interests. So now we've used the organic signal. We've built notions of similarities due to the organic signal by learning the psi embeddings all the way back here. So we know this is telling us organically whether items are similar or not. And we can also produce user representations here. And these are the two things we're going to pull forward when we're training on the bandit signal. But as mentioned previously, the bandit signal is very uneven. So we're going to need to borrow strength and use this organic information as powerfully as we can. And this is, again, it's due to the fact that the bandit signal is very strong on actions the previous version of the recommender system favored. But the organic signal is in fact strong everywhere. So we do know that we did not often recommend phones. Let me rephrase. We probably did not often recommend phones to people with grains in their history, yet we think this is probably a poor recommendation. And the only way we're able to get this information is the use of the organic signal. So we can't abandon the organic signal, even though the bandit signal is the one that is actually giving us the true calibrated notion of performance. So here's a quote from our paper that I think brings this out. The organic session might contain information that two products, say rice and a phone, are rarely viewed together in the same organic session. However, probably not contain many events where a phone is recommended to a user with rice in their history. If the recommended system is to infer that this is likely a poor recommendation, it must do so through a prior linking the bandit behavior to the organic behavior. So now I'm going to introduce the full BLOB model, which is a two-part procedure, in fact. On the left, we see the organic model, and on the right, we see the bandit behavior. Now, despite the complexity we see here, this is in fact nothing more than a logistic regression model. What happens here is we do the training here, we learn the embeddings, and we also learn the user representations, and we then lock them, which is strictly speaking, not a fully Bayesian approach. Fully Bayesian would be end-to-end, but it's a very useful pragmatic approach. And what we're going to do is, now that we know the user representation, which will be a vector of length k representing their interests, we have an action, and we're going to want to predict the reward or click for them. And above, this is clearly a logistic regression. Well, logistic if we use a logistic link function, because the reward click is binary. And we've got the parameters and bias term, parameters beta and coefficient kappa. We've got, and the heart of the BLOB model really is the use of a special type of prior that's going to allow us to borrow strength using the using side to put a, which is the organic embeddings, to put a prior on the bandit embeddings. We then have three hyperparameters that in some sense are not important because they're simply weightings of how strong various aspects of this prior is. So something important to note, when you see models like this, you should actually read them from top to bottom. And again, if we look at it here, and indeed we're now seeing a sigmoid, if we make this a logistic sigmoid, it is clearly a logistic regression model where we're taking the action A, the user embedding omega, and we're predicting whether there's a click received or not. We have, and I'll explain this in more detail in a second, a matrix normal prior here with three components. So matrix normal is a special type of distribution on matrices that can be understood very easily using the just normal multivariate normal distribution. And it contains three elements, the first one being a mean and two covariance matrices. Finally, we have the hyper parameters that we also put priors on. And these are going to control the strength of various aspects of this model. And as promised, this is how we understand the matrix normal in terms of a multivariate normal. So here, beta is a p by k matrix. M is the mean of it. It's also a p by k. R is a p by p matrix, and S is a k by k matrix. Now, if we flatten beta, we can see we have view this as a normal distribution with the mean also flattened, and we're taking a Kronecker product between R and S. We take a Kronecker product between R and S, we get a very large matrix, and in fact it needs to be, because this is now vectorized. Beta and M are now of length pk, and here we may have, if p is millions of items and k is an embedding size of 100, then we're getting a very long vector. You have a covariance between all the individual items. When you take a Kronecker product, you make these matrices very large. So it will have to be pk by pk. So the matrix normal, in fact, puts a very compact representation of this, because R and S are far smaller than R Kronecker S. So that's possibly fairly abstract, but there's actually some fairly clear intuition of how we can understand this matrix normal distribution, because each of these components actually have quite a lot of intuition of them. And each of them, of course, are highly informed by psi, which is learnt organically. And we're going to see, in fact, that there are three fundamental differences in bandit recommendation. There's the notion of, is there a large action history distance? So is this recommendation we're delivering similar to items in the user's history? And we're seeing that coming out in the first component of the matrix normal here. But and this is pretty traditional. I think it's the implicit assumption. In fact, when Flavian talks about proxy methods, effectively what we're assuming is a similarity in, like this, organically implies similarity in the bandit space. So it's really the assumption that this distance or difference is important. We also have action distances, and I'll talk about these more in a second, and history distances. And these second two don't give you anything a priori, but they allow you to use the bandit signal more efficiently once it arrives. I'll talk first about the action history distance, which is I think the simplest of them. And what we're seeing here is that on the left, we have the action or recommendation completely different to the history. And again, the action is completely different to the history. And on the right, the action and the history on the y-axis here are the same. And here, they're at least similar categories. And the mean in both cases moves upwards. And so that's all we're in fact saying. If the item we're recommending is similar to the item in history, then a priori, we think there should be more. Of course, how much more is unknown, and that's what the hyperparameter of WA here shows you, and sets that strength. So I think that's the most simple. I'll now go through action. And in terms of action, what we have is that if, what's important to note here is that the history, in all cases here, there's a single item in history. It's a view of the item beer. And on the left, again, there's no correlation between the items. So if we're recommending drone phone to someone with beer in their history, is what we're seeing on the x-axis. And if we're recommending rice to someone with beer history, is what we're seeing on the y-axis. And basically what we're seeing here is there's not much correlation. This is not centered around the diagonal. There's quite a lot of error here. And what that means is if we were to learn for some reason, perhaps we decided many times to recommend drone phone to someone with beer in their history, we may learn the click-through rate is, say, 1% or 2%, whatever it may be. It means actually we don't know much about what the click-through rate here is. On the other hand, on the right, if we were to recommend beer, a drone phone to someone with beer in the history many times, but we were instead to look at the recommendation of a city phone with someone in their beer history many times, and say we were to learn that it is 1%, then we can do a correlation across and say, actually, this prior says these are very correlated items. There's probably a similar click-through rate on both of them. And by doing this, we're able to learn far faster. So this is the case of action. In the case of history, it really is very much the same concept. Here you'll see the recommendation A is the same everywhere, where previously it was the history. So we're looking now at different contexts where you would recommend beer. On the left, we're seeing two different histories that are completely different, drone phone and rice. And what we're saying is, okay, if I was to learn, perhaps by doing it many times, the click-through rate of recommending beer to someone with drone phone in their history, it really doesn't tell me what the likely click-through rate of recommending beer to somebody with rice in their history. The items are too different. On the other hand, if we were to recommend beer to someone with their phone in their history many times, we would learn the click-through rate. We would actually have a fairly reasonable idea of what recommending beer to someone with a different phone in their history would be, just because they're similar items. They're likely similar people. They're likely to respond similarly to a recommendation. Of course, if we were to obtain lots of signals on both of these, it would override the prior. But in the absence of that, as mentioned previously, with bandit signal, you're not going to get good signal everywhere. So to some extent give a different view over this same point, I'm going to now look at a case which I think is quite a typical one, where we have a recommender system where we're recommending sleek phone to users that have sleek phone in their history. there's a good chance that many recommender systems will do this. And a different phone, the drone phone, we're not going to recommend it to them at all, so that we're seeing 0 out of 0. So we look at the likelihood function for this. What we're seeing is in the recommendation of sleek phone, history of sleek phone, we've got a sharp likelihood function. This is a 1% click-through rate, but the amount of data here is finite. We're only seeing 1,500 impressions and getting 15 clicks. So there's actually a certain range of plausible click-through rate here, from about 0.5% to 1.5%. In this axis here, the likelihood is completely flat because we've got 0 out of 0. In the center here, we've got a prior that seems like a not unreasonable one, like the one we saw previously, that's showing that these are similar items. We would expect similar click-through rates. Now, to do Bayesian inference, at least in simple 2D cases, it's very easy to say, okay, what we're going to do is multiply the likelihood by the prior to produce the posterior. There's an important point to note here that I think is good for intuition, is that when you're multiplying like this, it's much more useful to think about where is low than where is high. And the reason is, as you multiply low with high, you get low. So assuming that low is approximately 0. So we can basically say that the likelihood function here is consistent with anything in this direction, but is quite restrictive in this direction. The prior here, though, is saying, okay, we think the click-through rates are pretty low, and we really think it's correlated quite a lot. So when we do a multiplication and a normalization, what we see is that we get click-through rate on the item we're seeing lots of signal on it. It's reasonably narrow. We think it's about 1%. It's a little bit lower. That's because the prior is a little bit, if you like, pessimistic, in the sense of 1% is a high number. And there's also a fairly reasonable result here on recommending a drone phone, even though we've never seen it before, this range here. But it's wider, and but a basically plausible number. We can, and now imagine something that also might happen. This wouldn't happen all the time, but you would, in a big system with many products, you will see things like this all the time, though. And here we're going to say, okay, we recommend the drone phone 1 out of 1 time. Now, if it'll use maximum likelihood with anything, this would completely throw us off, because, in fact, this is now 100% success. And that's perhaps a not very accurate reading. Perhaps we just got lucky on this one time we did it. If we look at the likelihood function here, and it's actually a bit hard to plot, it's of course the same in this dimension, but because of the plotting and the contrast, it's a little bit harder to see. But again, it's going to be between 0.5% and 1.5%. And we've got a very gentle incline that's going to increase off the axis where this goes to 1, because of course it takes its maximum value at 1. In fact, the likelihood function is going to be just a simply line here. Again, we'll multiply by the prior, and as we multiply and renormalize, we get a posterior that looks sensible. It's of course moving up this way. Let me rock back and forth so you can see the differences. So it's coming up a bit. It's still basically reasonable. At this stage, it's not super clear which one you should favor, and the details of the priors and how you're setting them are going to impact this rather a lot. But we're seeing that it's not throwing you off completely, and we're getting reasonable signals. So the way in our paper, this is a table from our paper, well, the way we demonstrate the value of the BLOB model was to study cases where the organic was a very good predictor, particularly due to this first distance that we noted, so that basically making next item predictions as choosing the most likely item in a session as a recommendation was a good thing to do. And we also simulated cases where it wasn't always a good thing to do. Something useful about the RecGM simulator that we've developed and used here is that it allows us to consider bandit algorithms, so algorithms using the bandit signal and algorithms using the organic signal side by side. So the RecGM simulator is something we've been working on for a few years now, and it simulates sequences very much like the ones you're seeing in the example. So you're seeing an organic session followed by a bandit session, and your performance is given by how many clicks you achieve during the bandit sessions. So here we're able to, in flips equals 0, flips is a parameter that controls how correlated these organic and bandit signals that were simulated are. And we're seeing that the when their flips equal 0 and they're correlated, the organic methods, particularly the multi-VAE from Liang et al. And our BLOB model, do very, very well. The bandit signals do not do well. And this is because it's basically just a weaker signal and it takes a lot longer to learn on it. IMKNN doesn't do very well either. And our BLOB model that combines both signals also does well. But what's remarkable is that as you increase the flips and cause them to be decorrelated, the performance of the organic models basically have to fall, because you're ignoring the performance online of what actually happens. But the combined models also fall, but by far lesser degree. And so they're able to hold the performance using the bandit signal and borrowing strength to learn here. And okay, we do this study with different numbers of products, both 100 and 1,000, and obtain similar results. The combined signals are holding up. BLOB NQ and BLOB MQ are different variational approximations that we're employing here, and they have slightly different properties, but they both work quite well. So thanks for listening. In the following sections, we're going to look at a simplified version of this model that Sergey will take you through using the STAN language, and that's a really great way to do prototyping and understand the performance of your recommendation model, but only in toy situations. Then, so he'll give you an introduction to STAN, which is a Bayesian probabilistic programming language. And then Otmane, in the final section, will tell you how to scale this using TensorFlow and deep learning techniques. Thanks very much.
Welcome, everyone. My name is Sergey Ivanov. I'm a research scientist at Criteo, and today I will present a tutorial on recommendation and introduction to STAN. So we'll have two notebooks. One is more of just introduction to a language called STAN. In particular, we'll be using PySTAN. So you don't have to actually install anything. It's in Google Colab, and it will be instead installed automatically. And then we'll move to the second notebook, where we'll have more available examples for recommendation. So we'll define our own model, and we'll work with some product embeddings. So let's start with PySTAN. So we'll have a task of fitting a normal distribution. So PySTAN is a language that allows us to define distribution on the parameters and learn those distributions. It also allows us to set up some priors on the parameters. It's written in C++, so it should be fast, but it has some interfaces with different languages such as Python and R. And essentially, it's very simple. What you need to do is just to write what is called a script. So this is just a string, and the string should have some blocks. So there are several available blocks here, which are defined here. So you can have a block called data. So data is define the parameters. It's not even the parameters. It's the variables that obtains the data that we provide to it later. So it's like a placeholder for the data that we'll provide later. Transform data is another block, which is we define a function of our input data. And then there are parameters and transform parameters. So parameters define the real parameters of our model, and transform parameters define some functions of these parameters. So in parameters, we just need to specify the data type of the variable, while in transform parameters, we will specify the data type and some function of the original parameters. And speaking of data types, we have several basic types such as real, int, vector, row vector, and matrix, and some constraint types such as simplex, unit vector, ordered, positive order, correlation matrix, and covariance matrix. Moreover, we can have bounded variables. So we can put the upper or lower bounds on the variables. So for example, here, when we specify in this angle brackets the lower bound. So what we say is that the sigma variable is anything that goes from 0 to plus infinity. And you can do the same for upper bound. So that could be useful, for example, if you define some probability or some variance and so on. And finally, the only actually obligatory block is the model block. So this defines the priors of your parameters and what I call the loss function, but in fact it's log posterior of your model. So it defines how essentially your model should operate. And generated quantities, you can think of it as some variables that you would like to output, additionally calculate to your model. So let's take a look at a very simple basic example of Bayesian program. So what we try to do, we try to feed the normal distribution to our data. So as an input, we need to have 3 different variables. So one is n. N defines the number of observations that we have. And 2 additional vectors, vector of size n, y, and vector of size n, x. And this will define x the variables, the points, the observation that we have, and y is the target variable. And we will have 2 parameters of our model, alpha and beta, which will say that the mean of our distribution. So what we need to do is eventually we'll need to have a normal distribution with some mean variable. So this mean variable should be parametric. Those are the parameters that we try to learn. And here we have a unit variance. So this alpha and beta essentially are the scale of the input variable x, and alpha is the offset to this. So overall, it defines the mu, and mu is the parametric mean of our model. And finally, the model part here, what it does is we define the prior first on the parameters that we have, alpha and beta. And in fact, if you don't define the priors for your parameters, Stan language will do it automatically for you by setting the prior from minus infinity to plus infinity with uniform distribution. So giving the priors to your parameters is essentially giving you flexibility to apply your domain knowledge to the parameters. So for example, you know that some of your data has this variance, so you can calculate this variance and then set normal distribution with that variance. So normal is it's the function that is defined within Bayesian. We didn't define it anywhere here. And there is a good documentation at Bayesian which provides you all possible continuous and discrete distributions. So you can take a look at the documentation and see which functions can you use there. But here it's a very simple model. Essentially, we say that our input y should follow the normal distribution with mean mu, where mu is transformed input x and the variance 1. So let's run the code. So what we do, we first import all the required libraries. So the most important is Bayesian. So when you run this, it could take a while to actually install Bayesian if you do it the first time. And then we define this string, which will define our model. And afterwards, we run Bayesian Stan model, and then model code equals script. And this will compile into C++, in C++, this model. So let's run this. And usually it takes around a minute, actually, to compile it. But afterwards, once you compile it, it becomes pretty easy to provide any data that you have. So while we wait for the model to compile, I'll explain you the next part. So this is just a toy example. We have train model, train data, X-train, which follows the normal distribution with 20 examples. And then we have Y-train with X-train scale 3 plus 1. And we don't add any noise here, but in real world, you would probably have some additional random noise to Y-train. And by then, once you compile this model, so now you can see that the model is compiled. You can check what it is. Sorry. You can see that it's a STAN model, and so it has some functions defined inside this PySTAN model. So there are two most important functions, which is optimizing, and another is called sampling. This one. So sampling, what it will do, it will draw 4,000 samples, and for each sample, you will have some set of parameters, some values for your parameters. And then you need to take the mean of those across those samples to get the predicted parameters of your model. And optimizing is running MCMC, and it's deterministic, so you'll get the same result every time. So let's now try to run this model. So with sampling, usually you prefer to do sampling instead of optimizing. And what you just need to provide to it is the data that you defined here. So here you can see that you need to provide n, y, and x. And what you do here, you provide a dictionary with y, which is equals to Y-train, n, which is equals to the length of Y-train, and x, which is equals to X-train. And let's run it. And you can see that it runs pretty fast. So you get the data. Now let's do it maybe step by step. So let's first repeat this line here. So what we need to provide is the parameter called data, which will be the dict. And here we'll have several parameters. So it will be Y-train, and n, which equals to the length of Y-train. So let's run this. Okay, so it finished running those 4,000 samples. It's pretty fast. And now there is a command called extract. So you can actually check what fit is. You can see that it gives you the summary for every parameter that you have. So you have alpha, beta, and then mu. And for each one, you have mean, standard error, standard deviation, and then the percentiles, and some additional information here, how good your predictions are. So you can see that there is some explanation here. But if you just need to get the calculated learned parameters, then you need to call extract. And so we call this variable s. Let's take a look at s. S will be essentially your learned parameters. So this will be as another dictionary. So you can take a look at alpha. And remember that alpha is defined here, and beta is defined here. So here we see that it's an array. So let's check the shape of this. And you can see that the shape of this is that it's 4,000 array. So where this 4,000 came from. So this is default number of the number of samples that you have when you run sampling method. And therefore, if you want to get a real evaluated alpha, what you need to do is you need to take a mean. So here, when you define alpha, you actually define it as a scalar. So it should be a one-dimensional array. So what you need to do instead, you need to take a mean of this, and this is your alpha. So what it says to you is that alpha should be equals to 1. And let's take a look at beta. We'll also take mean. And you can see that beta equals to 2.99, while alpha equals to 0.99. And that makes sense because your original data has the factor 3 here, so it's very close to this beta factor, and 1 here as well. And in fact, if you look at the mu, so mu is also calculated here. Mu is this transform parameter. Remember here when we define mu, mu is essential alpha plus x times beta. So let's take a look at mu. So mu is this one, and because x is a what is it? It's a vector of size n. Therefore, mu should be of shape 4,000 by 20, because we have 4,000 samples, and for each sample we have 20 observations, 20 values for x. So what we need to do, we need to take a mean for the first dimension, 4,000 here. And if you do this, we'll get now an array of size 20, right? And this mu should correspond to actually y train. So if you take a look at y train additionally, you can see that it's pretty close between this and that. So that means that your model that you defined here converged, and now you learn the parameters alpha and beta. And of course, this is a very simple example. You can add additionally here the random noise, for example, following some normal distribution with epsilon variance. And in that case, you would get other parameters, and they would diverge because you have some additional noise. And now if you want to play with PyStan yourself, first of all, you can check this documentation for Stan language. And there are plenty of different tutorials online that you can explore. So this one, the documentation link that I sent here is on the exponential distribution, which explains you what is the command here and what parameters does it take. So essentially the command is exponential equals beta with parameters beta. And the exercise that I provide here is essentially you need to add additional parameter sigma. So in this example here, I defined a variance of the normal distribution equals to 1. Now I propose to you to have a learned sigma parameter. So now you just need to define a parameter sigma, and then define your log posterior model with this additional parameter sigma. So you'll have parameter mu and also sigma. So that's it on the first notebook on PyStan. Now let's get into the recommendations with PyStan. Essentially, we'll have 5 different products, which are books, journal, rice, salad, beer. And we are given some product embeddings. So for this exercise, we assume that they're given to us from some other program, algorithm, or job. For example, it could be SVD on a co-occurrence matrix. And so here you can see the product embeddings that we have. So let's take a look actually at those. How they look like. So the first row corresponds to the product called book. The second corresponds to the product called journal. Then we have rice, salad, and beer. So assuming we have these 5 different products. Now let's take a look at the product similarities. So for this, we just need to multiply each row with each row so that we have pairwise similarities. So with this, we'll see actually that this number corresponds to the similarity between product book and book itself. So everything that it lies on the diagonal is corresponding to this pairwise similarity between the product with itself. But then this one corresponds to the similarity between the product book and the journal. So you can see that the matrix is symmetric, and that, for example, book is not close to rice at all. This is because you can see that essentially these values, non-zero values that you have here, they don't overlap so zeros here don't overlap with zeros here. Essentially, your product similarity becomes equals to 0. Okay, so this just to give you a feeling with what type of data that we work. Now the model that we will work on, we will have the following model that were described in the slides. We will have the product embeddings, and we'll have the product embeddings multiplied by some learned parameter epsilon. And we have a weighted average between the two. And essentially what it means is that we have some organic product embeddings. So those, for example, learned by SVD, by just co-occurrence matrix. But we also additionally have some epsilon parameter that transform these product embeddings. And therefore, this multiplication, this product, matrix product, will be our bandit embeddings, or product embeddings with additionally getting some signal from the clicks or impressions that we have for the user. So this will be our organic embedding. This will be our bandit embedding. We take a weighted average between the two. So this V1 and V2 are also some input parameters that we are free to choose, or we can put them in parameters and then learn them as well. And then our model will be very simple. So we'll have binomial legit model. So let's try to actually find this binomial legit. So it should be here, I hope. Right. So coming back to this one, we have essentially this is the binomial legit formula. So after you take the log of this, you have some constant here, which is the log of the gamma functions. But then you have n times log logit raised to the power of -1. And this logit to the power of -1, this essentially corresponds to sigmoid function. So you can read it as a log likelihood, just a cross entropy, for example, in PyTorch or TensorFlow. So you have n times log sigmoid alpha plus n minus n log 1 minus sigmoid alpha. So this is a binary cross entropy. And the formula, the way it looks like, it's the following. So we have n and alpha. And let's get back to the examples here. So we have impressions n here. So I'll explain you later what impressions, but what I want to explain is that this defines our model, and the model is just the cross entropy of beta and user embeddings that we receive. So now let's get one by one actually for the script to get more understanding. So first of all, what data part do we have? Well, we have n number of observations. We have some number of products. In this case, we have 5. We have dimension, which is the dimensions of the product embeddings and of the users as well. Then we have clicks, impressions, and actions. So clicks and impressions, it will be the array of size n, where every element is the number of clicks we have for particular users, and number of impressions are the number of displays that we have for this particular user. And actions are the products that we want to show to this user. So let me maybe show you in more detail how data may look like. So we can have this log, and each log is just a list, right? And in each element of this is a dictionary. So we have A stands for action. So for example, what if we show a book to a user that has in the history a book already? So show the same product as the user already have seen before. And we say that the user has seen 1,000 different impressions or displays of the advertisement and 10 different clicks. Okay, so let's get back to the script. And then we have additionally user embeddings and product embeddings. Those are also given to us, so we somehow computed the user embedding of this dimension dim, and the same for product embeddings. And 2 parameters, as I said, just to define the beta function. Now, the parameters that we try to learn are the following. So we try to learn epsilon, some global offset, and some local offset that we call Rohde. So this will be different for every product. And now, what we will do in the model, we first define the priors. So this defines our priors for all our parameters. So for Rohde, offset, and epsilon, those follow normal distribution. And then we define our log posterior. So here we define it just in a loop with binomial logit, which will be our binary cross entropy. So it will be binary cross entropy between the number of impressions that we have for this user, then the dot product. And the dot product will be between the user embeddings and the beta. And the beta is actually essentially product embeddings, transformed product embeddings that accumulates both organic and bandit signals. And last, we add to it additional global offset that we also learn, and then some local offset pro. And finally, just to output, for our purposes, we generate quantities. So for example, we generate quantities CTR that for every possible product in the history and every possible action among all products, we compute what will be the CTR. And for that, we use inverse logit function by using the same dot product between users, between products, embeddings, and beta. So now let's compile this. I must say here that I defined some priors here, but I didn't explain how do we define it. So there is no strict way how to define the priors for a model. So the best way, if you have some intuition behind what should be the prior for your parameters. But the other way would be to set the priors so that the results that you have for some part of your data makes sense. So let's wait for this model to execute, and then I'll explain the rest of this. So next, what we'll do, we'll prepare the data. We'll have a log of different users, where every line consists of a history of the user, action A, number of impressions for this user, and number of clicks for this user. So clicks divided by impressions are essentially the CTR, or how likely the users click on the ads. We have a few functions that I'll not go into detail that prepare the data. And then we have some functions that plot the histogram of our recommendations. So let's first work with this simple example when we have 0 impressions, 0 clicks for every user. So you can see that we have all possible different combinations between action and history. So we assume that the history is consistent. It consists only of a single product. It's not required. In fact, you can put here book. For example, I don't know, a salad and book. So that means that your user had this history. But just for simplicity, I will work with this, and later you can play with different logs. So what you see here is that you have the users about which you don't know anything. You don't know how likely they click on the ads. So now let's actually prepare the data. So this prepares the user embeddings, which are just the weighted average of the things that you have in history. So for example, in the case of beer, it would be the embedding of the beer. But if you had more products here, like salad, for example, then it would take just the average between these two different embeddings. You have actions, which I defined here. You have clicks and impressions. So these three will be of arrays of lengths n, which is the number of users that we have. And user embeddings will be n times dimension, which is the dimensions of our embeddings. Right, and then we run model.sampling, and here we need just to provide the data as I explained you before. So we have v1 equals to 1, v2 equals to 0.5. So that means that here in clicks, in beta, sorry, you have v1 defined as 1 and v2 defined as 0.5. So you have less weight for the signal, for the bandit part. You can play with these parameters as well. You have clicks and impressions. You need to provide n, number of products, actions, dimension, product embeddings, and user embeddings. And then you do extract, and this is just the function that prints the best recommendation. So what you see here is that when the history is book, then it will recommend the book. When the history is a journal, it will recommend the journal. When the history is rice, it will recommend rice, and so on. So essentially nothing is learned from our data because there is no information about the users here. Let's maybe take a look more into our extract. So extract should give us the parameters of our model. And here we have parameters such as beta, row, offset, and also epsilon. So those are parameters that we defined here. They are now learned, and that means that we can actually compute what is the most likely recommendation for every history that we have. So this plot history function, what it does, it shows the CTR. So y-axis is the CTR for every pair, where the first product means the history, and the second product means the action or the recommendation that we want to do. So for example, for the history book and the action book, we have a CTR of 0.7. And this 0.7 seems to be very high. So first of all, this is error bars. So that means that the model is not sure about this particular use case, because we don't have any data in our log here. So it will be 0, 0. But also what we see is that this value 0.7 is pretty high. And this happens because the prior that we set here is offset, for example. It's pretty high. So if you change this to -8, for example, we'll see better values, like more realistic, more plausible values for CTR. And you might ask, how did we actually learn those CTR if you don't have any data for our users? And the answer is that it's fully based on the product embeddings that we defined here. So it uses the product embeddings, and it sees that we have the similarity between book with itself is the highest, therefore I will recommend the book, and so on. So this is particularly not very interesting example. Let's take a look at the example when we have some data about the users. So in this example, what I define is that we have a user with history book, and then you have 1,000 impressions for this user and 10 different clicks. And for the case when you have a book in the history and a journal as a recommendation, you have 1,000 examples and 20 different clicks. So you can see by looking at the first two rows that the user will likely to click on the journal, because the number of clicks here is more than when you show the book. So you expect that your model will learn from this bandit signals from clicks and impressions, better CTR, better prediction. So let's run this. We run the same model, so we just need to do sampling. Okay, so now we, sorry. Now let's take a look at extract. So again, we'll have parameters like, actually you can take a look at which parameters do we have. You have epsilon, offset, raw, beta, CTR. And now if you do print best recommendation, you can see that when the history is book, you better recommend journal. So this shows you that despite the fact that book is more similar to the book itself, you better recommend journal, because from the data, you can see that you have higher CTR by showing journal than the book. And finally, let's close the histogram. So now you can see that there are many interesting details. So for every color corresponds to some history. So for example, we have a history of a book. And here you can see that the CTR, first of all, is learned now to be of the values that are plausible. So it's of 1% or 2%. And now you can see that these green dots, they correspond to the predicted CTR. And this black crosses, they correspond to the real CTRs. And you can see that because the real CTR is higher for the journal than for the book, for this one, 1% for this one, and 2%. Now your green point, which is the predicted CTR, is higher for journal than for the book. So if we compare these two examples, so here it was shown that the CTR for the book should be higher. Moreover, the error bars were quite high, so it was going from 10% to 100%. So it wasn't quite sure in terms of its prediction. Now here with additional data, we see first of all that the error bars are reduced significantly, but also that your data actually pulls your predictions up. And that's great. That means that we both use the organic signal and bandit signal together, and the model is ready to be applied in real settings. And the final example that I want to show you is using what I call the unlucky log. So in this case, what I do, it will be the same log as before, so it will be the same log as here, except that now I will change this line, and I will say that for this line, I'll have one impression and one click. So in this case, this particular user has 100% CTR. But this could be a very unlucky event because you have very high CTR, but you have very few events like this. So you have only one event. So you could be just unlucky. Some user just accidentally click on your ad. And what you would like from your model is that it wouldn't actually change drastically because of the high CTR here. It wouldn't try actually to recommend book given the beer just because of this. And this is essentially the log that we have here. So now you have 100% CTR for the case when you have a beer in the history and you recommend the book. And we do again the sampling of the model, and then we do print of the best recommendation. And you can see that for this case of beer, nothing changed. So we still recommend the beer, which is a good recommendation, despite the fact that now you may think that the high CTR it would be for the book. So if we plot the histogram and take a look at the beer here, you can see that the CTR for book indeed increased. So first of all, you can see that the error bars are quite high for this case when you have a beer and a book as a recommendation, because you have only a single example. Now let's compare it to those. So in this case, your recommendation for book was the same as for the journal and for the rice and for the salad, because it didn't have any information for these cases. Now you can see that your recommendation for the book became higher than for the journal and for the rice. However, the variance is still quite high, and it's still quite smaller than for the case of beer. And this is expected because if you look at the data, here we have 1,000 different cases of impressions and 20 different clicks. That gives us better confidence than for this case when we have a single impression and single click. So you can see that the model is resistant to this small confidence recommendations. And finally, if you plot the epsilon, so what we do here, epsilon, remember, is our parameter of the model. And this parameter of the model, what it does here, it transforms the product embedding. So essentially, it shows how much do we need to transform our organic embeddings of our products. And so if you plot the standard deviation here of the epsilon, what it will do, it will, if this value is close to 0, it means that the standard deviation for this epsilon is low, and therefore we are quite sure in terms of our predictions. And if the standard deviation is quite high, then it means we are not confident in our bandit embeddings, let's say. And so you can see that the yellow points correspond to high variance, low predictions, and blue points correspond to high confidence. And therefore, you can see that, for example, the first product is very confident in their bandit embeddings with respect to itself and to a second one, but because it doesn't have any data on 3 other products, it's not confident at all, and so the variance is quite high here. And just to wrap up, there is a small exercise, which is add to the initial script additional generated quantities that compute CTR, not just for a single product in history, but for all possible pairs of products in history. And the question that we need to answer is that we need to plot CTR for all possible pairs. And you can use the same function as before, plot hist. And to answer how is it different from when you have a single product. So essentially what you need to do here is just to add additional generated quantities here. Before we were defining it for, let's take a look here. Before we were defining it for when you have a single product in history and when you recommend some product. Now what I want you to do is when you have 2 products in history and you recommend a product, and then plot the results and see how the results are changed with respect to the history when you have a single product. So I hope you got the main message about this model, is that if you have this model, you take into account both organic and bandit signal, and therefore it's resistant to small number of occurrences of some recommendations in your history. And therefore, it could be a good model that you can use for your use cases.
Hello, everyone. My name is Otmane Sakhi. I'm a first-year PhD student in Criteo AI lab working on probabilistic modeling applied to recommendation. I will be presenting the second notebook of Bayesian value-based recommendation, where we try to shed light on Variational Bayes, which is a powerful tool to scale Bayesian inference for problems with high dimensionality on large data sets, as we encounter in real-life recommendation problems. My colleague Sergey went through the basics of STAN and the intuition of the model built by trying it with different data sets. Our purpose here is to do a quick recap of the definition of the model with STAN in the same simple setting of 5 products, present its results rapidly on a log dataset of impressions and clicks, in the goal of comparing them to the results of the scalable alternative that we're going to suggest here, which is Variational Bayes, that is completely implemented in TensorFlow. Building on the same setting, we have 5 products: book, journal, rice, salad, and beer. And with embeddings here, with product embeddings that state that journal and book are somewhat similar rice and salad are similar, and beer is independent from the rest. And we have a log data set here where we recommend one product from the 5-item catalog, to users with histories of one product, and we observe clicks. So here, for instance, in this first line, we recommend a book to a person with the history book. We do like 1,000 impressions and we get 100 clicks. This block here is where all the utility functions are defined, and they help us either prepare the data or plot the results that we get. If you remember correctly from the previous notebook, this block here defines the model in the Stan language. So Sergey did a great job explaining the script and the model, but I'll do a quick presentation of the important parts. So here, this part is where all of the priors on the different parameters are defined. And here, this is our model, which is a logistic regression with parameter beta that should encode the similarity between the user embeddings and the actions or the products that we recommend. Here we have a global offset that calibrates the model, and here Rohde, which is a local offset that encodes the contributions of the products or even banners on the click independently from personalization. So the particularity of this model is in how beta is defined. The intuition is that without any impressions, beta needs to pull strength entirely from the product embeddings. So here we have this epsilon with a prior set to 0, meaning that if we don't have any data set, we're gonna stick to our prior, and all of this part will get canceled out. So beta will mainly be the product embeddings that we have before. And with more and more data, we update these product embeddings to learn a value-based model that is accurate and risk-averse. So beta is built as a linear combination of the organic product embeddings and a linear transformation achieved by a matrix called epsilon here of those same product embeddings that is learned based on the logged data of impressions and clicks. Here, we assume that W1 and W2 are fixed for simplicity, but they can also be learned for better flexibility of our model. So let's go to the next block. Here, this block here just rearranges the data to fit it into Stan and fits the Stan model with a powerful Markov chain Monte Carlo method. If you're interested, it's called Hamiltonian Monte Carlo, and the algorithm used is the no U-turn sampler, which is a very fast sampler considered as an exact method for its accuracy. Here, of course, we just plot the results to see if they make sense. And here, for example, if the history is book, from our model, we recommend the book. If the history is journal, we recommend the book. If it's rice, we recommend the salad. If it's salad, we recommend rice. And for beer, we recommend the same, which is beer. Exact sampling method, like Hamiltonian Monte Carlo, for example, give near perfect results when the size of the dataset is small and the dimensionality of the problem is in the order of hundreds. And of course, if the target distribution is easy to sample from and doesn't really have a lot of modes and some geometry that is really hard for the algorithm to explore. In real-life recommendation problems, well, these conditions are not met, and we treat datasets of millions of records with a dimensionality that is at least linear on the number of products, meaning that these methods will suffer from incredibly slow conversion time, and we will need faster methods to infer our model's parameter. So in this tutorial, we're gonna try to present the idea behind the variational Bayes and the method of reparameterization trick that will allow us to transform the problem from an integral computation to an optimization problem that can leverage GPU acceleration easily. Well, I think that there are many ways to derive the objective of variational Bayes, but I like this one as it's intuitive and presents the method as just a reduction of something exact but difficult to manage or do. So the first equation here is trivial because the closest distribution to the posterior in terms of a Kyle divergence is the posterior itself. So we have this equation here, and the KL can be KL between this Q distribution and the posterior can be decomposed to get an expectation over Q of the log likelihood and a KL term between the prior and the distribution we are looking for, and a constant as well that we omit here as we're looking for the minimizer of our objective. This equation is called the negative elbow, and its minimizer in the space of distributions is indeed the true posterior. So what variational Bayes tries to do is, instead of doing this optimization in the whole distribution space, we choose a parametric family to make the computations tractable. A common choice of the family of distributions is the multivariate Gaussian for its simplicity and asymptotics as well. So the problem becomes of looking for the best Gaussian here that minimizes the negative elbow. Here, these blocks are just where we can import libraries, and here we gonna install TensorFlow 1.15 as our code is not compatible with TensorFlow 2.0, and one can have fun turning it into TF 2.0 if he wants to. So here, the elbow has two terms. In the first part, we're going to focus on the KL term between the variational distribution and the prior. If you remember correctly, the prior we chose for all of our parameters were Gaussians. And as we're using Gaussian variational distributions, we can leverage closed form between a closed form of the KL between two Gaussians that we know how to compute easily. And the second term here is an expectation of the log likelihood under the variational distribution. And here what we propose is a trick called the reparameterization trick, which is derived from this simple result here. And with it, one can build a stochastic version of the negative elbow that doesn't need to evaluate all the data set in each iteration. So this method helps us achieve faster inference as it's stochastic and can leverage GPU acceleration easily, as it just becomes an optimization problem here. In the next blocks, we just define our objective and run a classical optimizer, which is the ADAM optimizer for 100K epochs to obtain results here that we're going to try to compare to what we got from the MCMC runs by Stan. Here we compare the means of the distributions that we get from both MCMC and variational Bayes. Well, at a first glance here, we see that the patterns learned are equivalent, and the spectrum here is pretty much identical. And even if we plot the learned means side by side, we can see a close to perfect correlation here. So that's good news, meaning that VB learns the mean correctly. For the standard deviations of our distribution, which are here to help us identify the uncertainty in our learned parameters, we can see that both patterns of MCMC and VB are similar, but here the spectrum of the values covered is different. And if we plot both standard deviations side by side, one can clearly see that VB here underestimates the variance of our distribution, giving us bad estimates of uncertainties compared to HMC, which we consider our gold standard. One can explore the different means and NCDs for the rest of parameters. Here, for instance, we have the offset, the mean of the offset with different algorithms, but if one wants to explore the different means and NCDs for the rest of the parameters, feel free. And the rest of the parameters are, for instance, the offset and Rohde. And one can see if we can observe the same behavior here. So I hope this little introduction to Variational Bayes applied to recommendation was clear and fun to follow. If you're interested in the subject, you can explore more advanced methods in our paper BLOB that was published in KDD 2020 and play with the code in the following link to produce the results. Thank you for your attention, and of course, if you have any questions, don't hesitate to contact us.